I now call to order the Society's 2,469th meeting in what is now the 151st year since its founding on March 13th, 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends, including everyone here in the Powell Auditorium at the Cosmos Club, and everyone tuning in on Zoom and on YouTube to tonight's lecture by Brett Denevi and Wesley Fuhrman. The Society is grateful to the sponsors of the 2022-2023 lecture series for their support, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who was asked to remain anonymous. And we're also grateful to the sponsor of tonight's lecture, who's in the audience, but has asked us to have them remain unnamed. So please join me in thanking all of our sponsors. Speaking of sponsors, as mentioned at the last meeting, the Society has begun a fundraising campaign to ensure that we will be able to meet expenses in the coming years without having to reduce the number of meetings and lectures and without having to spend down reserves. The goal is to raise $20,000 more in dues, contributions, and sponsorships than was raised in previous years. So far, we've had some modest success, but there's a long way to go. If you can afford to contribute by sponsoring a lecture series or an individual lecture, please let me know. And even if you cannot contribute financially, let us know of anyone or any organization you know who might be interested to support the Society. Feel free to email me at president@pswscience.org. That said, back to our program. I'm pleased to announce the following new members. Michael Nord, scientist at the Johns Hopkins University Applied Physics Laboratory, interested in planetary science, remote sensing, human spaceflight, astrophysics, very particularly synthetic aperture radar, and space resources, who learned a PSW from a friend. Mary Lark Lovering, a program analyst, retired from the Department of Housing and Urban Development, interested in urban planning, land use, transportation, sustainable development, housing standards, and housing choice, who learned a PSW from attending PSW meetings. Michael Sandifer, principal with Open Field Capital, interested in software, quantum computing, biotech, and ceramics, who earned a PSW from PSW President Larry Milstein. Mike Selnick, electrical engineer, retired from the U.S. Postal Service, interested in engineering, astronomy, nature, and health sciences, who learned a PSW some time ago from his longtime friend and PSW member S. Fred Singer. And tonight's speakers, Brett Denevi and Wes Fuhrman, who learned a PSW from our invitation to speak here tonight, and whose interest will be clear in part from tonight's lecture. We welcome them to membership. If you're not a member and would like to join PSW or support the Society, you can do so through the PSW website using the blue Join button on the upper right-hand corner of the homepage. We welcome new members and we appreciate donations. So please join now. All members are entitled to wear the PSW Science Rosette, The rosettes are $15 plus 90 cents DC sales tax. They can be purchased online or at the rosette table in the back of the room. Please note that rosettes must be picked up at a lecture at the Cosmos Club. Why? Because PSW cannot mail them to all over the country and be responsible for paying the individual sales tax that may prevail where they mail them. Before we turn to the minutes of the last meeting, I want to take a few minutes to remember PSW member Adarsh Deepak, who passed away unexpectedly this past week. Adarsh was a scientist, an entrepreneur, an author, and an educator. And he was an enthusiastic member and supporter of PSW, who sponsored several PSW lectures in recent years. Adarsh's son Ravi is also a PSW member, and our sympathies go out to Ravi and all of Adarsh's family and his friends. We here at PSW have lost a good friend, and our thoughts and wishes are with you. Incoming Recording Secretary Camille Lance will now read the minutes of the 2468th meeting and the lecture by Sean Gulick on deep impact and the Cretaceous mass extinctions. Camille, the stage is yours.
Thank you, Larry. On December 2nd, 2022, from the Powell Auditorium of the Cosmos Club in Washington, D.C., and by Zoom webinar broadcast on the PSW Science YouTube channel, President Larry Milstein called together the 2468th meeting of the Society at 8:02. He welcomed new members, and the recording secretary read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Sean Gulick, a research professor at the University of Texas Institute for Geophysics. His lecture was titled, "The Latest on the Great Dinosaur Extinction." Gulick began his talk by expressing gratitude for being invited to discuss the Cretaceous Paleogene extinction event, which he argues is the most important event in the last 100 million years, because 75% of life went extinct, including the pterodactyls and the T-Rexes. Gulick then introduced impact events, highlighted the heavy bombardment period, and told a story about a father and son who wrote a paper in 1980 which claimed that a 12-kilometer-wide asteroid hit the Earth and caused an extinction event about 66 million years ago. This was based on an iridium spike in an Italian limestone formation. The speaker went on to explain evidence which confirmed this claim. He explained that the International Ocean Discovery Program went on Expedition 364 in order to understand the impact of craters, their environmental impact, and how they affect habitats. The Chicxulub impact crater was studied, a roughly 200-kilometer-across crater at the edge of the Yucatan Peninsula, provided a means to understand impact cratering processes. The seismic profile of the crater and three-dimensional modeling showed directionality and angle of impact. The worst combination, Gulick admitted, for the survival of the dinosaurs. The expedition collected sediment over 3 months, and the sediment was sent to 4 labs. The same iridium anomaly found in Italy was determined to exist in this crater, correlating the extinction of the event and provided a timestamp. Gulick notes that by definition, the Cretaceous period ended the moment the asteroid struck. He then discussed the layers of rock they identified through analysis of their collection. One layer, the speaker highlights, was made of melted rock which could only occur under a pressure on the scale of 60 gigapascals, or 10 billion times the energy of Hiroshima. Gulick then briefly notes how this research is related to human exploration through space. Namely, the sampling of peak rings actually means sampling the lower crust of bodies such as the moon. Expedition 364 confirmed that impacts caused large target rocks to flow and resurface planets. The collaboration determined that this extinction likely occurred due to transmission of sediment through the atmosphere. Specifically, the impact caused volatiles to permeate the atmosphere, including 300 gigatons of sulfur, and about 400 gigatons of carbon dioxide, likely causing sub-zero temperatures to span from 10 to 15 years. This impact winter prevented photosynthesis, reduced the food supply, and caused starvation. This starvation was the likely cause of the mass extinction. Grulich explained that this impact caused surface extinction. However, the organisms in the seafloor continued to thrive on ocean-dwelling algae. The speaker then compared the amount of sulfur and CO2 released from the impact to the amount that humans generate. Humans, he noted, generate a comparable amount of CO2 approximately every 4 years. However, humans have in total generated orders of magnitude less sulfur than the impact. The third objective for Expedition 364 led to the analysis of the peak ring using geophysical data to identify the velocity of sound through the rock as a way to probe habitats. The team found that thermophilic life favored the environment produced by the impact for around 10 million years. In fact, astrobiologists on Expedition 364 analyzed the cores of the samples taken and identified living cells. They also extracted active DNA from multiple layers, demonstrating active thermophilic life, which likely succeeded from the ecosystem generated by the impact. He concluded by noting that the impacts are a driver of life and ubiquity in the universe. Next, the question and answer period began. One of the members asked about the homogeneity of particles in the atmosphere as a result of the impact. The speaker explained that the climate change was global, but the local refugia was inhomogeneous. Everything larger than about 60 pounds went extinct. So even if there were refugia, they were not large enough for the larger species to survive. Another member asked about the effects of a similar-sized asteroid hitting the land area of Earth today. The speaker highlighted that if the Chicxulub crater, the Chicxulub asteroid, hit either the Pacific or the Atlantic Ocean at the time that it hit, then the event would have largely caused a water vapor event and not caused such large extinction event due to the lack of volatiles. When considering a land impact, a similar consideration of volatile-rich impact region must be considered. Humans would only be wiped out if there was large enough of a climate event created. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 9:57 p.m. The temperature in Washington was 8 degrees Celsius. Weather was partly cloudy. The number of streaming and online viewers and in person was 118, and views on the PSW and YouTube and Vimeo channels alike in the first 2 weeks of the lecture was 584. Respectfully submitted, Cameo Lance.
Thank you, Cameo. Do we have any comments on the minutes? Any corrections? If anyone has any questions about the lecture, they can watch the lecture on our Vimeo YouTube channels, which they can get to through our website. But hearing no suggestions or comments on the minutes, I will entertain a motion from a member to accept the minutes as read. And we have a motion. Do we have a second? All members in favor? All members opposed? The minutes are accepted as read and will be posted to the website in due course, subject to any corrections necessitated by comments transmitted electronically within the next day or two. We now turn to tonight's speakers, Brett Denevi and Wesley Fuhrman, and their lecture on plans to return to the moon permanently. Brett is Principal Staff Scientist at the Johns Hopkins University Applied Physics Laboratory, Deputy Principal Investigator of the Lunar Reconnaissance Orbiter Camera, co-investigator on NASA's ShadowCam instrument on South Korea's Denevi orbiter, and co-investigator on the upcoming Lunar Vertex and Lunar Vice missions scheduled to land on the moon in 2024 and 2026. So we're especially appreciative that she's taken the time to be with us tonight. Previously, Brest served on the steering group of the recent National Academy's Planetary Sciences and Astrobiology Decadal Survey, as vice chair for the panel on the Moon and Mercury, and as the science chair of NASA's Lunar Exploration Analysis Group. Her research focuses on the origin and evolution of planetary surfaces, particularly the volcanism, the effects of impact cratering, and space weathering. She's an author on more than 90 technical papers on her work, and among other honors and awards, she is the recipient of a NASA Early Career Fellowship and 7 NASA Group Achievement Awards. Asteroid 9026 Denevi is named in her honor. Brett earned a BA in Geological Sciences at Northwestern University and a PhD in Geology and Geophysics at the University of Hawaii. Wes is lead for the Lunar Surface Innovation Initiative at Johns Hopkins University Applied Physics Laboratory. His APL work involves lunar and cislunar space, hypervelocity impact sensing, and modeling and advanced materials. His physics research focuses on condensed matter physics, in particular spectroscopy and theory of topological quantum materials, theory of strongly correlated materials, bulk crystal growth, characterization and analysis, and device fabrication in lab-grown single crystals. He is an author on several dozen technical publications on his work, and among other honors and awards, he was a Schmidt Fellow. He earned a BS in physics at UC Irvine and a PhD in physics at the Johns Hopkins University. All questions will be fielded after the lecture during the Q&A session. Brett, the stage is yours.
All right. Thank you, Larry. Got it. All right, I am really thrilled to be here to talk about the moon tonight because every day is a good day to talk about the moon. But today in particular is special for a number of reasons. The image on the right here was taken exactly 50 years ago today. That is Jack Schmitt and Eugene Cernan on their way back from the moon. The trans-Earth injection burn was about an hour ago, 50 years ago today, after they completed the Apollo 17 mission at the Taurus-Littrow Valley. And exactly 1 month ago today, the SLS launched on its Artemis 1 mission. This was 2.5 weeks ago, the Orion capsule with the Earth and the moon in the background. 11 days ago, beautiful images during the close encounter with the surface. And just last Sunday, splashing down the Artemis 1 mission. So we're finally going back. It's really happening this time. And it does feel like with the successful completion of the Artemis 1 mission, that we are on the precipice of a new era at the moon. And I think we've been saying this, it's been said before, but this time we're really doing it. So the last US robotic lander, kind of shockingly, was in 1968. The top right image there is from the Surveyor 7 lander. And then, of course, the last crewed lander 50 years ago. And now, in the next 3 years, the United States has 13 landers planned. We shall see if they all happen precisely within those 3 years, but that's a really remarkable turn of events there. That includes 1 crewed mission. The Artemis 3 landing will be the first mission to return people to the moon. And then there's a whole host of other orbital investigations ongoing, as well as other international exploration efforts. So what changed? Why this sudden increase in activity at the moon? A lot of that is coming from the Space Policy Directive 1. from 2017. This was what set us on the path for Artemis. This was a statement that the United States would lead an innovative and sustainable program of exploration, return of humans to the moon for long-term exploration and utilization, followed by human missions to Mars and other destinations. I've also included a quote here from our current Vice President. The Artemis program will establish the first space station in lunar orbit and the first lunar base camp, an artist's rendering of which you can see there. I kind of hate artist's rendering because I've been looking at these for a very long time. But here is one that could be the Artemis base camp. And it will train the first mission to Mars. And it's notable that this Artemis program has now spanned 2 administrations, because previous efforts to return to the moon did not. So what is sustainable exploration? That is really kind of the key to what is different this time. The goal is not just to return astronauts to the moon, land, look around, come back. It's to send them there to build a sustainable presence. So you can define this in various ways. The definition that I've included here is we provide our working definition of sustainable as meaning there are widely accepted reasons to continue human lunar exploration that justify the continued investment, commitment, and risk beyond a few missions. The reasons to continue the lunar program include ongoing scientific discoveries, investing in potential commercial development, technology development, educating the next generation of STEM professionals and a scientifically literate public, and inspiring the public about our individual and collective opportunities and future. And so I'm highlighting now a couple of areas that we will talk about tonight. I'm going to discuss the ongoing scientific discoveries that the Artemis program will make possible. And then Wes is going to be covering the commercial development and technology development aspects. And these words come from the National Academies, which does NASA asks every 10 years that they do a kind of consensus study of what are the important science questions in a bunch of different fields. Here it's in planetary science and astrobiology. And so they come up with a list of these important topics and then some suggestions for how to answer them. And for this most recent decadal survey, which it was released in April, we defined some of the largest questions that can be the science themes for lunar exploration. And if I can make the pointer work, we will focus on 2 of these: solar system history and water and volatiles, both of which are related. And they touch on sort of the bigger picture science that can come from the moon. These are questions that are not just of interest to lunar scientists, but to a huge variety of interdisciplinary studies. Okay, so why is the moon so good at telling us about solar system history? The moon provides a really great record going back very far in time, essentially to its beginning with an impact that created it. And so that's a 4.5 billion year history. I'm showing here in orange all of the craters on the moon that have been mapped out that are larger than 5 kilometers in diameter. And so you can see there are a lot of them. Many of them are very, very large. If you contrast this with the Earth, the previous talk sounded extremely relevant. But the Earth has a pretty small record of impact events. These are the mapped impact events here. I should note that their scale is vastly exaggerated. The largest impact crater known on Earth is about 200 kilometers in diameter, and you can see there are just really a handful of craters known on Earth. And that's because of all of the things that go on Earth that make it a fun and exciting place to live. Life, weather, wind, erosion, plate tectonics, all of that going on. Earth is not a great record keeper of its own past. It's constantly erasing its surface. So these are some of the more recent impacts preserved in Canada, and you can see how degraded those are. On the bottom there is a picture I took inside of one of the most famous and most well-studied impact craters on Earth. It's the Reese impact crater in Nordlingen, Germany. It's about 24 kilometers in diameter, and it formed 14 million years ago. 14 million years ago is like yesterday in geologic time. And look at that crater. Isn't it stunning? It looks like a field. And you contrast that with what a crater on the moon looks like that formed much longer ago, 110 million years ago. This is the Tycho impact crater on the moon's southern near side. This crater is about 80 kilometers in diameter. It formed 110 million years ago. So the dinosaurs, if they were paying attention, could have looked up and seen a preview of their fate on the moon there. But the details inside of this crater are pretty stunning. They include this giant central peak. The impact energy was so large, this asteroid or comet was coming in at more than 10 kilometers per second. The energy it released compressed the surface down so far that this central peak then rebounded up, forming in just a matter of minutes. And that thing is 2 kilometers tall. Surrounding that peak is a sea of frozen impact melt. So the rock was melted by the impact, formed this sea of molten rock, which is frozen there around the central peak. If we zoom in here on the central peak, these images are from the Lunar Reconnaissance Orbiter camera, provide really stunning details. This boulder here in the middle of it, that is about the size of a football field. So pretty immense and stunning feature that is so well preserved, it looks like it formed yesterday. So this is why we look to the moon to understand our history, because all of the craters that were forming on the moon, an analogous population was forming on Earth. The same impactor population was hitting the Earth. And so we can look back not just 110 million years, but we can look back to billions of years ago. This large basin here, the big circle in orange, is over 1,100 kilometers in diameter. And this basin formed by a large impact about 3.84 billion years ago. And how do we know that number? Well, the Apollo 14 mission landed on the Frau Moro Formation. That formation has been mapped out as Imbrium Basin Impact Ejecta. And so the Apollo 14 astronauts went and they picked up that rock. Hopefully you can see the circle around it. That is sample 14051. It is one of many that date the Imbrium impact event. Here is the same rock in the lab then, and they can date that rock, which was melted by the impact event, resetting its radiometric clock, and get those ages. And when we look at all of the various places that samples have been returned from on the moon, the yellow stars are showing the Apollo sample return sites, and then the Lunar robotic Soviet sample return sites. I should note, I did not update this slide. It is missing a star now. There is the Chang'e 5 sample return site over here. It sampled a young volcanic region. Very interesting, but it doesn't contribute to this very ancient story. So when we look at these ages, we've dated the Imbrium impact event, 3.84 billion years. Serenitatis, thought to be 3.89. Crisium, another huge impact event, 3.89. Nectaris, 3.9 billion years ago. This is really interesting. why are they all about the same age? And that age is actually quite young. It's ancient, but younger than it should be. And that is because we think that when the solar system formed, it pretty rapidly swept up all of the planetesimals, the larger debris was, coalesced into planets in a pretty short order. So this is about 600 million years later. Why is there this large population of impact events, impactors striking the moon, and by corollary, the Earth at this time? So this is known because it is late into our early solar system history as the late heavy bombardment, or also the lunar cataclysm. And so this is a notional diagram of what that would look like. But here's where the impactor population was high right after solar system formation, declined rapidly, and then you had this spike right at 3.9 billion years ago. So this was, a big mystery for a while. Where is this impactor population coming from? Until there were several different dynamical models that started to explain how this would happen. So this little animation will loop through a few times. It's kind of mesmerizing. But this is called the Nice model. It was developed by several people all working in Nice. And so the colors here, this is showing the orbits of just the larger planets. So Jupiter is in red, Saturn in orange, Neptune is in blue, and Uranus in purple. And all of those green dots are the icy planetesimals of the Kuiper belt. And if you look, well, there's a lot to look at here. I guess my pointer has too large of a dot to point out specific features. But the blue there is Neptune, and it is way inside of where it is now. And so what these series of dynamical models all show is that at some point, Jupiter started migrating outwards. It got into a mean motion resonance with Saturn, which then caused Neptune to be kicked out. It just kind of plowed through the Kuiper belt like a wrecking ball, sending these icy planetesimals scattering throughout the solar system. And so according to the Nice model, there's various other models now. This is Nice 1.0, there's Nice 2.0, there's the Grand TAC. These are all kind of known as giant planet migration. They predict various details differently, but this is the main story of all of them. All of them are predicting that the lunar cataclysm, or some type of cataclysmic event, was part of a solar system-wide heavy bombardment. And so this is an artist rendering of what that would have looked like on the early Earth. Very hellish. The early Earth during this bombardment period would have been an inhospitable place. We heard a bit about the Chicxulub impact effects. Now take that and make it, many, many more times larger and happening every few million years. The fact that it is predicted to happen around 3.9 billion years ago is also really important because we think that is right when life was beginning to form on Earth. And so how that insane impact bombardment would have been shaping the Earth's habitability and really destroying its habitability for periods is really an important factor in understanding how life emerged on Earth. These impact events, like Imbrium of that scale, would have vaporized the Earth's oceans, created temperatures that could sterilize the crust. So did life have to emerge multiple times? Did only the strongest survive? Is an important question that a lot of people who study the origin of life focus on. And the other reason this is quite fascinating is because it has implications for the origin of Earth's water. There are a lot of ideas about how the Earth got its oceans. One kind of popular idea is this late veneer model, where the Earth was, largely formed, but there was a late veneer of water delivered to it. And so if you have these icy planetesimals being scattered, material being scattered in from water-rich asteroids, comets, that is one model for how Earth's oceans came to be. So this is the neat and tidy story of our impacts, all spiking around 3.9 billion years, which we know from samples. We can put that into this big late heavy bombardment scenario, and then dynamical models that explain how that came to be. The problem came in the last 10 to 15 years or so, and a lot of this actually came from the Lunar Reconnaissance Orbiter. Until 2009, when we first started getting data back from LRO, we really didn't actually have good global imaging of the moon. The best imaging came from pre-Apollo lunar orbiter missions that actually took high-resolution images on Polaroid strips, which were developed on the spacecraft and scanned and sent back. So not the highest technological advance compared to what we can do today. So when we started getting images back, that enabled a whole new series of geologic investigations. And those included a look at the effects of impact basins. For example, the moon is rotated here. This is Oriental Basin on the western limb. It's younger than Imbrium. It's one of the biggest young impact events on the moon. And mapping out these plains in yellow that surround the basin. Most of these were shown to be ejecta from the Oriental event. So you can see just how widespread this event was and how catastrophic and world-altering this was for the moon. When we started looking at some of the other landing sites, for example, the Apollo 17 landing site. This is a view from Lunar Reconnaissance Orbiter. On the top right here, this is showing the Taurus-Littrow Valley. The lander was right there in that valley. And some of the samples that were collected, this is geologist Jack Schmidt collecting a sample from this rock. We can see that rock from orbit. It actually left a little trail as it rolled down a hill, and that's that little series of boulders there 50 years later. When we look where that rock came from and other samples like it, they rolled down these large massifs. And when we map out the bigger geologic picture, we can see that actually this looks a lot like Imbrium ejecta covering these hills. So this was our date for the Serenitatis impact event. We may have actually been looking at Imbrium samples again. And then another development, kind of post-Apollo that took a while to build was from the lunar meteorites. The first lunar meteorite was identified in the 1980s, and then all of the trips down to Antarctica to find those meteorites have built up a collection of over 500 lunar meteorites now. Those provide a more random sampling of the lunar surface. We don't know exactly where on the moon they came from. We don't have their geologic context that would give them more meaning. But when we compare their ages, hopefully you can see in yellow here is the Apollo samples with this big spike right at 3.9 billion years ago. Hopefully I can see the lunar meteorites are in blue. Their ages span a whole range, asteroidal impact events that have been dated from asteroid meteorites because this was a solar system-wide bombardment event, don't show a particular spike at 3.9 billion years either. So now this whole scenario that I've just explained to you has been called into question. And the question now is, was there a late heavy bombardment? Was there a spike in impactors at that time? Or have we been going around the lunar near side picking up samples from a single impact event that has really radically shaped the near side. And so if we don't know the answer to that, that really just totally opens up what was happening in the early solar system. We have our original kind of late heavy bombardment. There's kind of various sawtooth type proposals that would be due to, disruption events of an asteroid that led to a big peak in impact events. Or maybe you just had a more steady decline from the early solar system. And so how are we going to solve this now? It's going to take a lot of work. Clearly, we've sampled a lot of different parts of the moon, built up a whole story, and now we're questioning the whole story. So what are we going to do? Well, I've turned the moon up a bit here so that you can see the moon's south pole down here. And did not get into this at all, but the moon is very geochemically fascinating. This map shows the thorium abundance. And so a lot of these kind of rare earth elements, incompatible elements, heat-producing elements, they are all concentrated on the moon's near side. And we think that these may actually be a pretty good tracer for Imbrium ejecta. So we want to get very far away from there, bring back samples for the first time with geologic context from an area, maybe like the South Pole, where the Artemis 3 landing site will be. The other story is looking at the South Pole Aitken Basin. This is now the far side of the moon, again, tipped up to show the South Pole. This basin is not very inspiringly named. It stretches from the South Pole to Aitken Crater, so it's the South Pole Aitken Basin. But it's about 2,500 kilometers in diameter, and this is the oldest known, all can agree upon its existence, basin on the moon, and the largest. And so dating the formation of this impact event, which has not been contaminated by Imbrium, which could put a bookend on that early bombardment history, is a big priority for lunar and for planetary science. So at the South Pole, this is how we will do that. The South Pole is ancient terrain on the moon. It has been totally beaten up, and the entire moon's surface, but especially these ancient areas, are covered in regolith. It's a just rocky debris layer that's created by impact events. Geologists really love this size scale. These are kind of centimeter-sized pieces, and showing all these different rock types, each one that can kind of date potential events. And so you'll be building up in these older terrains a new kind of statistical sampling of impact events that hasn't been as affected by the Imbrium impact event. And I should mention too that lunar scientists love the regolith. It is a treasure trove of scientific information. Don't listen to Wes later when he tells you the regolith is an annoying problem that will only, gum up the works of everything on the surface. The other unique opportunity that will come from the lunar South Pole is just its environment. So this is a simulation that is showing what it would be like to look out at the horizon from the moon's South Pole. You'll see the Earth kind of bobbing up and down. It's upside down, so you'll see Antarctica on the top there. And then the sun is just going to be sweeping around the horizon, always very low on the horizon, with these huge shadows being cast. If we kind of turn this now and are looking at a region of the South Pole, the simulated illumination from straight down, you can see as the sun, this is kind of sped up a time, so about a month will pass while I'm talking. You're seeing these shadows sweep across the surface. And if you stare at this long enough or take enough snapshots in time, you can start to map out areas that see a lot of light and areas that never see sunlight. And those are the permanently shadowed regions. And so this area near the moon's south pole, this is Shackleton Crater here. Its rim is right on the South Pole. This is an illumination map that we created by just imaging the South Pole over and over and over and over, and then kind of averaging out in time how often terrain is illuminated. So the white areas see a much higher fraction of light than you would see at the equator. The black areas are in permanent shadow, and they have been in permanent shadow for billions of years. This is a temperature map of the South Pole. Wes will get into this more, but these areas are very cold. The blue areas on this map are all have maximum surface temperatures below 100 Kelvin. And so that is so cold that you can trap any volatiles, water. As you get colder, you start trapping more exotic species of volatiles. But these cold traps happen when you would have a comet impact. Water molecules would be bouncing around the surface. If they hit one of these cold regions, they will stay there. And so Lunar Reconnaissance Orbiter, other missions have really worked hard to understand what is in these cold traps. Is there water ice? Because it should be stable at the surface. And so I won't go into the details too much because I think Wes will as well, but we have neutron measurements showing where we have signatures of water. NASA slammed a upper Centaur stage into one of these permanently shadowed regions, watched the ejecta of that impact event, measured its water content at about 5%. We've looked at reflectance spectra, and all of these little blue dots show areas where we see signatures of water ice. And then, actually, just when I was sitting there a moment ago, I got the email that the Korean Lunar Pathfinder orbiter has completed its lunar orbital insertion burn. So there is now a new lunar orbiter as of this evening. We have an instrument on there called ShadowCam. It will map out the permanently shadowed regions of the moon in incredible detail at about 1 meter per pixel, using light that is just kind of scattered off of nearby terrain. So it's a very sensitive camera. And what are we going to do with all of this information? Wes will tell you about all of the very useful things that you could do with this water ice. And I will tell you about the kind of interesting things that I would like to know from it. The main thing is its origin. If it has been there for billions of years, it's going to be providing a record of the delivery of water from the outer solar system, potentially, to the inner solar system. So it could also tell us about this kind of scattering of icy rich materials early on in time. There are various isotopic ratios you can look at, the D to H ratio, oxygen isotopes. Putting these all together, you can start to get an understanding of where this water would have come from if it came from the outer solar system comets in particular. And so this is going to be a really hard story to piece together. I mean, there is water there. Understanding its origin will be tough because it's been gardened in by later impacts. A lot has happened in the billions of years since it was deposited. And so we'll need to do a lot of work looking at kind of these patchy deposits of ice that may be buried or just adsorbed onto the surface in some areas, because these the distribution of this water is thought to be so patchy because of reworking, there's been a lot of thought into planning out, all right, what if we had a robotic traverse that would go very long distances, look at a lot of these different cold areas, compare what we see in craters that have been trapping volatiles of different ages. Older craters are going to give you that older record. And then from Artemis at the South Pole, eventually we hope to be able to return cryogenic samples. So this is an Apollo, well, it's an X-ray of an Apollo core sample. We'd like to get core samples from these permanently shadowed regions, preserve them at cryogenic temperatures, and return them to Earth. Also, not a trivial thing to do. And so this is where we would like to go to do this. This is one of the landing regions that NASA has announced will be a potential site of the Artemis 3 mission. They have not narrowed it down yet, so there are others, but this one is the best. This stretches between Shackleton crater right at the South Pole to de Gerlache, and has a very highly illuminated ridge, so there's a lot of illumination throughout the year on this ridge. Shackleton, de Gerlache, and some of these smaller regions are also in permanent shadow. This is about 30 kilometers across. The Artemis 3 astronauts are not going to have a car. They're only going to be able to walk a couple kilometers. So this is going to be something that needs to be built up, exploring this region over time, something that's going to take technology development, infrastructure, and there I will turn it over to Wes to tell you about that.
Thank you very much, Larry. Brett, that was fantastic. Really appreciate your talk and set me up so well. I won't say that all the stuff is bad. It's actually all going to be useful, for the most part. So there's actually a terrestrial analog to the sort of long-duration science that Brett was talking about. She even mentioned it in a couple other contexts. This is a very important place to a lot of lunar scientists. It's McMurdo Station in Antarctica. And so this gives us an understanding of the sort of science that you can take on if you have the infrastructure to stay and take on that science. And actually, we're thinking about how we could do that on the lunar surface as well. So through the Lunar Surface Innovation Initiative, we're working with NASA to help motivate the technology developments that you would need for this sort of long-term, sustainable exploration of the lunar surface. And here you can see how it's been broken up into the different technology areas. Let's see if I can get this going. Good. So you can see there are 3 that are more environmental. Dust mitigation, which I'll come to in a little bit, extreme access, getting to these places, extreme environments, the complications that come from being not in our nice little protected home here on Earth. And then there's 3 infrastructural ones as well. So surface power, how we're going to power all the things we want to do there, excavation and construction, so we can get the sorts of samples that we need and move the things around and do all of that. And then ISRU, which stands for in situ resource utilization. And that's how we can do all of this stuff without having to bring it all from Earth, right? That's a pretty important thing. We only have so much that we can actually bring or even fit within fairings. And so one of the natural questions that you can get to when we're looking at what we're doing in this 50 years later return to the moon, you know, history rhymes. So what is so different from this? We've got rockets, we're going to the moon. It's largely the same place it was 50 years ago. What is so different here? Well, it's not that we haven't been doing anything in those 50 years. In fact, there's been extraordinary activities, largely on the commercial side. So in 1969, when we first got there, there were about 159 active satellites around Earth, and in 22, we've got about 5,000. So there's this extraordinary rise in space activity, and that's driven now largely by commercial markets. And so one of the really interesting things is that instead of being in an era of spin-off technologies and NASA kind of having to forge all of the way, we're in an era where commercial is actually leading the way. And this is actually happening not just in low Earth orbit, but also all the way extending to the lunar surface. So here I'm showing a picture of Astrobotic's Peregrine lander. Astrobotic is a company that's one of the commercial lunar payload services providers. And this is how NASA can just pay for access to the moon. So it's a commercial company. In the same way that they're delivering crew and cargo to space station with commercial, with SpaceX, they can now deliver payloads to the lunar surface. So I will mention that the first launched commercial payload to the moon is likely to be iSpace, but it'll be a proper space race because they're taking a really slow route to get to the moon. And Astrobotic is launching later, but may actually arrive to the lunar surface first. So what we see is a really extraordinary development that NASA doesn't have to be the only ones leading the way. So while Astrobotic and some of these other commercial lunar payload services, these landers are going to go to several different places on the moon's surface, the preponderance of activities is moving towards the lunar south pole. And so what I'm showing here now is a view of the potential landing sites for Artemis. And you can see they're all around the south pole. I actually really agree with Brett that this connecting ridge right off of Shackleton is a wonderful place to go. And I'll say why in more detail as we go along here. So just to give you a little bit more on Shackleton, because I do think this is a great place to be, here you can see its scale laid on top. So we've got the DC region here laid on top of Shackleton. So we're deep in this permanently shadowed region here, which kind of feels like it this time of year. But yeah, you can see it's quite a large feature, but it's not nearly as big as some of the other ones that Brett was talking about. So when I think about huge features on Earth, I think about the Grand Canyon. That's my hometown. And it's about 4,300 feet deep. So that's pretty big. I can imagine it would be hard. That's some extreme terrain to navigate. But Shackleton's actually more than 3 times that deep. So it is a very, very deep, very dark hole with extraordinary questions to be solved if we can get in there and start exploring it, right? So Brett had already talked a little bit about how these permanently shadow regions arise. So you can see, I won't linger on this slide too much, but you know, instead of the 14-day night cycle, we have dark for billions of years in those permanently shadowed regions. And here's a view showing a little bit more to quantitatively the solar visibility averaged over a year. So you've got the permanently shadowed regions, which are these dark spots here. This is the connecting ridge that we've been talking about a few times. So one thing, if you stare at this plot for long enough, or these sorts of figures for long enough, you'll realize is that adjacent to these are these spots where you've got kind of a lot of illumination over time. That's a really interesting thing to see, and I think it's a little bit poetic that the darkest spots are closest to the lightest spots. But if you look here, you can see how those temperatures are changing over the course of the lunar day as well. So in the dark regions here, you can see those are the permanently shadowed regions. Adjacent to them, that's where the light is sweeping around. And what you want to note from this figure is that as those colors trace their way through this landscape, they go very, very quickly from being cold to being very warm. So as the sun, so the takeaway from this is that when the sun is on you, you're quite warm, and then as soon as it's off you, you cool down very, very quickly. So if you're in the dark, even if it's for a brief period of time, you're going to be cold. And that's borne out here as well. You can look at the min, mean, max of these plots, and even in the hottest part of the lunar summer, you still got your very dark regions where there is permanent shadow staying nice and cold. For those volatiles. So Brett's talked about how we can see that there are volatiles in these regions. So when I did my PhD, I actually studied a lot of neutron scattering, and my advisor said neutrons don't lie. So they know that there's water there, but they don't tell you everything. In particular, they don't tell us enough about what quantity of water there would be. We don't have the resolution to know exactly where it will be within those permanently shadowed regions or its distribution, right? So this is quite important because if we want to try to get this out, to take enough samples, to maybe somehow do something with this ice, we need to know its distribution and its form. The actual abundance is really important too, because if you are trying to extract some of this ice, if you have below about 5%, maybe if you're well below 5%, you see you climb up this energetic cost where you have to spend a lot of energy just heating all the rest of the regolith in order to get the water out. But once you're above about 3% or so, then you can see you're actually putting most of your energy into actually extracting the ice itself. And so there's an interesting question. If you've understood the science of this through looking at isotopic ratios and things, what else would you want to do with it? Well, you could drink it, for one. And I think it would be a really astounding thing to see astronauts sustained by something that they've sourced from off this planet. But the other thing that you can do is you can split it apart into hydrogen and oxygen. You can breathe the oxygen, of course. But once you've split apart hydrogen and oxygen, you can, of course, reverse that reaction as well. And here's a picture of a Delta IV rocket doing that in spectacular fashion. Right? So when you combine hydrogen and oxygen, you've got your rocket fuel. And so if you can split apart that, if you can get to substantial quantities of that lunar water and split it apart, you can make propellant. And you can use that propellant to bring yourself back from the moon. You could use it to take yourself even further into the solar system. So this is down the path of using the resources that we could get off planet to do more things. That's a key part to exploration. It's not just taking everything with you, but sourcing it from the places that you're going. So here's just another view of that permanently shadowed regions. And I'm going to focus in and change the scale here of the color plot. Here it's from 0 all the way to 1. I'm going to cut it from 50% on up. So this is where your illumination does better than an arbitrary place on the equator, right? So this is where you're getting a lot of light. And these regions of extended illumination are really quite small. They are these tendrils, essentially, that are around the permanently shadowed regions, and especially pretty well distributed along this connecting ridge. So if you want to rely on solar power to do a lot of the activities that you've got, which is probably going to be how we're starting all of our exploration, you're really going to want to be spending your time in these regions where you've got a lot of light and you've got a lot of warmth. So if you can move around, you can do better than just what we had on that last slide, any one particular location. And there are some really great methods for doing detailed traverse planning to increase your percentage that you're in the light all the way to well over 90%, up to about 95%. And one of the interesting things about this is you can realize that not only is that traverse just keeping that particular thing warm, but if you were able to lay transmission lines and put up stationary towers, you would have a distributed networked power system which has that amount of illumination as well. And this point is not lost on the people who are developing these technologies. So right now there are 3 companies that are developing these vertical solar arrays, which are meant to be deployed at the lunar South Pole or near the South Pole, where they can capture that very low angle light. And they're each 10 kilowatts. So that's getting to be the point where you can actually do some reasonable work with them. And all of these providers are also looking at how you could create a lunar grid out of this. So these are not just intended to be isolated elements there, but actually put in some of that foundational infrastructure that you need to do sustained development. But even 100 hours without light will get you cold to the point where you couldn't survive. And so how you can get power without the sun, basically you're limited to whatever energy storage you could have, but batteries are way too heavy. You can do fuel cells too, but they're pretty tricky. And so one of the best ways to get to it is with nuclear power. And so NASA's investing in fission surface power. This is the latest call has 3 companies developing 40 kilowatt systems, which can operate for quite extended periods of time, years or more, without having to touch them. And so there's an interesting question. Okay, so I've talked a lot about the power. How do you actually get it around? There's going to be two main ways that you're going to get it around. You can see tethers. That's quite nice if you're on the surface and you know exactly what you're going to do, point-to-point servicing and so on. You can also beam the power. So power beaming is another area which is a little bit foreign to us on terrestrially, mainly because we have an atmosphere, we have other easy ways to get the power around. But on the lunar surface, if we're trying to bring things across this really, really infrastructure poor location, beaming the power directly to where you want it is another option that's quite appealing. Excuse you. There's a lot of development that's going on in power beaming that's not just intended for the lunar surface. Here's a demonstration done by NRL along with Power Light Technologies. The general problem with power beaming with lasers is that the efficiencies tend to be low. But if you've got an awful lot of light at the rim of the crater and you only need 100 or so watts deep down in, then it turns out you can suffer that inefficiency without too much problems. But maybe this seems still like science fiction and you want to just do cabling. But that is still a highly non-trivial thing to do as well. So again, we're not protected by all of the wonderful environment that we have on Earth, and so we have an awful lot of radiation that you're subject to when you're on the moon. And what happens if you have a charged particle, an ionizing bit of radiation that crashes through your device, it will leave a wake of electron hole pairs behind it, and that will cause this huge transient in current, which will wreak havoc on your power system. So in addition to all of the other things that are impacted by all of this, even just getting your power across the surface is quite tricky. And so now I've talked a whole lot about power, and I believe that we can actually move it around generally, but what are we actually going to use this for? Creating the infrastructure is going to be very energy intensive. This is a picture from Boston Metal showing some steel production. This is extraordinary amount of energy that goes into this. And in particular, steel is an interesting thing because we're working to decarbonize it, and one of the methods that we have to do that, carbon-free, other than the energy that you put in, is called molten oxide electrolysis. So the only ingredients that you need are your ore and electricity. And so in the same way that you were splitting water into hydrogen and oxygen, you can split your iron ore into oxygen and steel. And so there's an interesting thing that you can do if you're on the moon. You've got oxides and silicates, and you can put those into this same type of reactor. And now instead of molten oxide electrolysis, it's molten regolith electrolysis. And instead of steel coming out, you still have oxygen coming out, but instead of steel coming out, you've got a whole bunch of metals that will come out as well. The actual metals that you'll extract will be dependent on, well, not only the composition of the regolith that you put in, but also on the energetics of the oxides as well. So the more bound up the oxygen is, the harder it is to extract. So you can actually do a little bit of benefication with this process as well and start to extract out preferentially those different metals, all while getting your oxygen, which you can use as well. Oxygen, by the way, is also about 80% of the mass of rocket fuel as well. So if you only wanted to bring up your hydrogen or methane, for instance, you could still source your oxygen half portion of the rocket fuel, even just directly from the regolith. And that regolith is going to be anywhere you land on the moon. About 40% of the moon by weight is oxygen. So you have no problem getting these components wherever you land. Here's a little picture of what it would look like if you wanted to have a complete system to produce oxygen like this. You've got an excavating razor excavator here, which can move 90 kilograms of regolith. It's got these interesting dual bucket wheels because you don't have the reaction mass that you would on Earth, so you have to dig in both directions at the same time. You've got your dual bucket wheel excavator. Uses a spiral vibratory conveyor. This is quite well known for how it would behave on Earth. You could drop it into your much smaller molten regolith electrolysis reactor, and from this be able to produce on order 10 metric tons of oxygen per year. And so one of the problems is still the electrolysis. You know, we know that it can work. We see industry is doing electrolysis even on for steel production. We see it. We use it all the time on water to get oxygen and hydrogen. Well, That's also harder on the moon. Not only do you have reduced efficiency in producing this in lunar gravity, but the bubble detachment off your electrode is going to scale non-linearly with gravity. And the big problem with that is if those bubbles don't detach, your electrolysis is going to be stalled. And so the volume of those bubbles, you can see scales to -1.5 on gravity, and this is the diameter of those bubbles as well. So all of those things conspire to the fact that you'll need an overpotential, a higher overpotential in lower gravity, and you run the risk of stalling your electrolysis process. But nonetheless, there are ways to get around this if you can test and if you can develop this. So that's what Space Technology Mission Directorate is working on, is developing these sorts of tests and these sorts of demonstration units that we can use to uncover these problems as we go on. And of course, one of the biggest things is all of your technologies are going to need something to work on and act on. If you want to do electrolysis, you need some lunar simulants. If you want to figure out how you can make your excavator work, you need some lunar simulants. And these vary dramatically both in composition and morphology, depending on where you source them. So if you look in particular on some of these, the very, very smallest pieces of these lunar simulants might border into what you call lunar dust. And dust is, it's quite pernicious on the lunar surface. It gets everywhere, it sticks to everything, it gums up your gears, it will break things. And in fact, the last person to walk on the moon said that I think dust is probably one of our greatest inhibitors to a nominal operation on the moon. I think we can overcome other physiological or physical or mechanical problems except dust. So Gene sort of laid the gauntlet down, saying that dust is the biggest boogeyman that we can have, and it's our problem that we have to solve. But even dust mitigation is something that we can address. And in fact, we can use some of those tricky problems that it has against it. So as I said before, dust is very electrostatic. It will stick to everything, but you can use that to actually repel it as well. So this is an electrostatic dust shield, and by applying a 3-phase electrode pattern, you can basically walk the dust right off using that electric potential. And so here you can see a very dusty set of these EDS, electric dust shields. And on the right, once you run this EDS process, it will just push it right off. And these can be made flexible, can be put in front of your solar panel, and so on for protecting. So, of course, this is not the only dust mitigation strategy. There's a whole host of things to do with this. But what you can see now is that we've pretty much walked through all of these general technology areas, and I've done kind of a blast through all of this. I should say this is a work of thousands of people who are trying to solve these problems. It's not just a few of us, which I think is an amazing thing, that we can all come together to solve this massive problem. And so, we're getting to the point now where we see a light and we see a sustained effort towards building this infrastructure where we can get to the moon and continue to do things for long periods of time. And so as we come to, as we've now passed this 50 years away from the moon, I want to end with this quote and then give a little visual for us to watch as well. So, as I take man's last step from the surface back home for some time to come, but we believe not too long into the future, I'd like to just say what I believe history will record, that America's challenge of today has forged man's destiny of tomorrow. And as we leave the moon at Taurus Littrow, we leave as we come, and God willing, as we shall return, with peace and hope for mankind. So if you'll honor Brett and I for just a minute, and I'd like to take just a minute to watch a video, just a minute for each decade that we've been off the moon.
really beautiful job, and it usually has music, Claire de Lune.
There is music that goes with that, but we couldn't use it because of copyright concerns. It will be picked up by YouTube, who will immediately shut down our well, it could shut down our feed, and they will monetize. And you have no idea what kind of advertisements they'll put up, so. But it's pretty spectacular, even without the music. So we have time for some questions and some answers, presumably.
Hello, Matt Kaywood, member. This is, I think, more for Brett. But you know, if you're trying to differentiate from that, you know, all these very interesting rocks come from either a single incident or a serial bombardment, you know, knowing the error bars on the dating would probably be very helpful. So, you know, do we have any hints on kind of the structure of the dates versus the range of error bars associated with those?
Yeah, so it's pretty easy to date the younger ones, right? The ones young here is, you know, 100 million years, maybe 1 billion years old, because they haven't been so beat up. When you get to those really ancient ones, the ones we really care a lot about, then it is hard because you have rocks that have seen a number of different impacts. And so the way that that's typically dealt with is looking at a series of different isotopic ratios. Like argon ages are that isotopic system is more easily reset. So it's going to typically record the younger ages, whereas maybe samarium neodymium is going to give you the older ages. But some of it does come down to kind of a statistical look, where you're going to have, you know, a bunch of rock samples, even, you know, they've been formed into new rocks, impact breccias. Pick those apart, pick out pieces of the regolith, and then you're dating and looking for, all right, where is the preponderance of ages for this geologic unit? The oldest ages are going to date that main event in that region. So that's why it, you know, it's not as clear cut as we've been to each site. We know an age. That's why we'll need to keep kind of digging at this story.
Bob Terry, I'm a member. A couple questions. All your DITI ports that you show, where is the radiation shielding? And aren't you really worried about this 1 to 10 MeV proton that's going to come visiting periodically from the sun?
Yes, absolutely. We're worried about radiation, and actually, you know, that's something that, you know, radiation shielding. Are you thinking more for human health? It actually plays a role in human health for sending our astronauts back. We're going to limit the amount of time that we've got there. It plays a role in our systems that we've got. There are basically two ways that you can address these issues on the technology side. The human health side I can't really address. On the technology side, you can make them robust to these sorts of radiation, which tends to mean just making bigger units. So on your switches, you might make a really thick epitaxial layer. The other way that you can do is solve it with redundancy and designing for repairability. So if you've got backplanes, you can pull one unit off and swap a new one in. That matters an awful lot because some of these events, as you said, are stochastic. You're going to get one sometime. You don't know if it's going to be day 1 or day 10. And so designing...
Or day 1, 3, 5, 7, 9.
Yeah, or day 1, 3, 5, 7. Exactly. You're exactly right. So that, I mean, that really underscores the importance of designing for maintainability from day 1.
Okay, so is there a plan for the humans?
For the humans, that's not my purview.
That's another expert. Another expert?
No, so
Regolith is an excellent radiation shield.
Water is a phenomenal shield too. Moderates. Hydrogen's a great moderator for that. Generally, yeah. We know the ways that we can protect ourselves from the radiation. You know, the exact set of using those tools on the moon is, you know, still a TBD thing. Yeah.
One thing that they do too, though, is, you know, just monitoring solar activity through satellites, and, you know, if there's a big solar storm coming, you know, get in your shelter.
Right.
Right. What's your shelter going to be made of? I guess is
You just bury it in a little bit of regolith, you're
Yeah,
fine.
you have to
Yeah,
do a
so-
lot of digging and then
Yeah.
and so forth, and that's a lot of energy
It is.
and a lot of material to be pushed up there that you don't necessarily make. You don't make your spacesuits from probably the local material.
No.
Stuff like that. And another question, of all the minerals I saw,
Right.
all these things are retorting to produce oxygen.
Yeah.
How much oxygen do you need per astronaut per year, and what minerals are best for it?
Right.
I once saw and talked about and wrote about ilmenite as a very good source.
Sure.
Is it still thought of as that?
Yeah. So the nice thing about some of the extraction techniques that we have is that they'll work on most of what you'll stick into it. Sort of like Back to the Future. You throw your trash in your engine, you get the thing out. The real driver for in situ resource utilization is not just astronauts, supporting astronauts. You can do ECLIS and recycle your oxygen that you're breathing out as well. It is to really get to the point where you're producing substantial amounts for propellant. That's the real big driver. And so then you can do some back of the envelope calculations and figure out, well, if I want to have this many back and forth return trips, it would be nice if we had this much coming from the moon. And actually, there was a workshop that we held a couple of years ago on sort of the supply and demand side of that. And it looked at several of the providers who would hopefully be playing in the game of returning and going back and forth to the moon, and they were saying on the order of hundreds to thousands of metric tons per year would be their demand signal. But this is a very difficult thing for us to get to that point, right?
My name is Scott Matthews, and I am a member. And I'm going to cheat and ask one question of each of you. So first, how do you get high-resolution maps of thorium abundance on the moon, and where did all that thorium come from? And then the other question is, in terms of surface nuke power, are you talking about RTGs, or are you talking about some other kind of reactor? And would beta voltaics play a role?
But which question is for which person?
We know.
I'll take the thorium.
Brett always goes first.
Well, that thorium map actually came from a mission called Lunar Prospector. It's 1998, I think. Kind of before the current era. But they had a pretty low circular orbit. I think their lowest altitude was around 30 kilometers. Gamma ray and neutron spectrometer that was able to map out some of that. It's still not super high resolution, like 30 kilometer kind of spatial scale. But where did all that thorium come from is like my favorite question. Thank you for asking that. So this goes back to the very kind of earliest formation of the moon. You had a magma ocean. As that magma ocean was solidifying, the highlands, the anorthosite, feldspar minerals, they floated to the top. They formed the highlands crust. The iron-rich minerals generally sunk down. Your olivines, pyroxenes sunk down to the mantle. And in between that, the last stuff to crystallize was this little dredge of incompatible elements. Your rare earth elements, thorium. It actually has a great acronym, CREEP. Potassium, rare earth elements, and phosphorus. So this CREEP layer is sort of sandwiched as this incompatible stuff left over from in between the crust and the mantle. So how does it get on the surface? Some of it is through volcanism, incorporating it, bringing it up. Some of it is exposed by impact events. There's a whole other interesting question of why is it so concentrated on the near side? There's not very much on the far side. That's a good question. We don't really know. So maybe there was a giant ancient impact that exposed a lot of this on the near side. Maybe there was degree 1 mantle overturn, all kinds of ideas we don't know.
And then to the suite of nuclear technologies. I think this is actually a really important question because I think often in the public there's just this idea that nuclear is one sort of thing, but it's extremely rich in the sorts of technologies and the way that you can extract energy from this whole suite of processes, right? And you hit on 3 of them. So I'll try to work my way up the scales, right? Starting with beta voltaics, which I think you would generally consider for lower energy, lower power scales. So for instance, I know of one that's being developed using tritium as a source for betas, right? So that's one way to get to them. And there's some other developments for very, very small stuff where you just need a little trickle charge to keep something alive or keep clock running and so on. Stepping up, you start to get to RTGs, radioisotope thermoelectric generators, and those we have for all sorts of deep space missions, and they can do all sorts of wonderful, wonderful things. We typically use plutonium for that, and that's a very precious resource. Getting it allocated to do something on the moon is sort of like it would be a pretty big lift, but there are alternative isotopes that are being developed for that as well. So that's sort of the next case where you're using the thermoelectrics. You can also do dynamic conversion of heat coming off of a radioisotope. That would be something like a dynamic DRPS, dynamic radioisotope power system. NASA's been developing those for a while. Previously was the Advanced Stirling Radioisotope Generator, ASRG. That's great because your efficiencies go up once you start to do it with the dynamic conversion instead of worrying on the sort of solid state side of things. And that has the ability too, you could develop with some of these alternative radioisotopes as well. The UK is looking at using americium. It's kind of ironic to me that the UK is using it instead of America using americium. Anyways, so that would be a great way for us to get into that hundreds of watt scales. But the real sort of game changer that could happen, and there's a very significant amount of effort going into it, is actual fission. And so when you're doing fission, you're talking now controlled reactions, where you're actually stimulating it, you've got some control, and the neutron population able to, to basically moderate your power system over time and really control how much you want to get out of it. And that's where you're starting to look into the tens of kilowatts and beyond scale. So NASA's FSP, fission surface power, RFP that they have out right now, there are 3 companies that are performing on this, 3 teams I should say, all developing 40 kilowatt systems. This is really interesting because they're being built on not highly enriched uranium like we use for the Navy, but high assay, low enriched uranium. So this avoids non-proliferation issues. There's tons of investment going on this on the terrestrial side for micromodular reactors. So there's a whole lot of efforts that are all kind of coalescing together that will make that more likely to succeed. So I'm very excited about the prospect of having, tens of kilowatts worth of power that you can take anywhere the sun don't shine. And so going really far out, going down into PSRs, having power no matter what cycle the light's in, that's all very, very, very big change if you can have that sort of scale of power.
I'm going to go take a question from our webinar audience. So Carl Merrill, can you please unmute your mic and ask a question?
Hi, thank you, Larry. Throughout the talk, maybe I missed it, but I didn't hear anything about astrobiology. And it seems to me those deep places where water may or may not collect would be a spectacular place to look for something like that, number one. But also there are dangers in that because a lot of astrobiologists think that that's how the Earth got seeded, that it takes too long to make the kind of life we're accustomed to in the 4 billion years that the planet may or may not have been able to sustain it. And so it may be drifting through the whole universe and then settling in different places. And of course, that's the kind of thing that scared Michael Crichton to write his book. To do that, first of all, you have the problem of having the proper precautions for this, and secondly, what efforts are being made to look for this?
Yeah, so in those really cold areas, we do think there are probably some organic molecules, and this interesting place to look at this abiotic organic chemistry going on. There are various planetary protection protocols in place, both for protecting the Earth from samples brought back from elsewhere and also protecting, other places. The moon is in one of the lowest restriction categories. The poles have particularly the permanently shadowed regions that's been looked at again recently, and oh gosh, what was the outcome? I mean, they added a little bit of protection, but it's still unrestricted generally. We're not super concerned about any, life there, but there is a lot of worry about contaminating those volatile, organic, rich deposits before we can really understand that ancient story. Because of course, well, there's probably already some contamination from Apollo landers and things, but sending a big lander right down near the pole, you're definitely going to be contaminating it with your rocket fuel. So there is a lot of work and concern in these areas. It's not my area of specialty to really dig into the details on that for you, though.
I'm just worried that you may be underestimating the possibility of life, because there was just an experiment published recently where they showed that radiodurans, which is an extremophile, can repair radiation damage and can withstand the radiation for 380 million years on the surface of Mars. Here you're not talking about the surface, you're talking about in a deep pool. So if that model is true, then there's a good chance something dropped in there. And it may be different than what we're used to. And I certainly hope we take that seriously.
Yeah, so I'll say just one more thing on that. I think it almost, not only Michael Crichton, but it also feels like Lovecraftian, of like this billions of years old place. But the temperatures down there are really such that whatever is happening is pretty well frozen. At some point you are fighting physics in terms of what can be the sorts of processes you can go on there. We're also not sending humans down in there, and I think the main thing that we'll be trying to do with going into those permanently shadowed regions is to bring back as well controlled of samples as we possibly could.
I'm not worried about it replicating in there, I'm just worried about it trapping in there.
It's a subject for another presentation.
Hi, my name is Frederica Derima, and I'm a member. Thank you very much. Very exciting presentation, end-to-end kind of topics you addressed, mother lode for kind of investigations. So you presented a very ambitious infrastructure. I assume there is some kind of a roadmap of, incremental. I mean, certainly there will be experiments that will be done here to validate things, but also as this infrastructure, is it prioritization of what items you're going to, in a sense, start kind of installing, testing? What is the timeline? Is it 50 years?
No, these are wonderful, wonderful questions. And I was sort of chuckling because they're the questions that we're pushing on trying to understand as well. So I'll say that NASA has recently released something called the Moon to Mars objectives. This is something of an exploration version of a decadal. So that's something that's relatively new for NASA to do. It is new, and it's hopefully really going to encourage the sorts of cross-administration consistency that we've seen over a couple administrations now. That's what we need in order to make this happen. This is trying to capitalize on the momentum that we've developed. And that roadmap, that's a Moon to Mars objectives. It's not a roadmap yet. I do expect that a roadmap will be coming out within the next 2 months or so. That sort of timescale. They are intending to continue to work that kind of a roadmap. But even just sort of sketching out what timelines you think most of these things are happening, we tend to have some date at which we expect the technologies will be at a state where we could hand them off to flight. So that's all very well controlled. And I mean, it's literally thousands of technologies that are being developed. So each of them are in different sorts of stages and different categories. Understanding that infusion, huge effort that's undergoing for all of that. I'll say that the way that I think of sort of a minimum time at which NASA would be able to or need to be using the moon as a proving grounds for whatever it wants to do would be at least a couple decades. So some of the things that I talked about, like the fission surface power, that's probably not going to be done until 2030 or so. It's not going to go straight to Mars to provide power there, and that is a really Mars-forward technology. it's going to need to go to the moon for a while. So even just those sorts of things where the moon has to be the place where it goes first, that's going to ensure that there is some longevity to being on the moon, returning. It's, you know, it is a large cost to go to the moon. It's coming down very, very rapidly, but it is absolutely microscopic compared to trying to put this stuff on Mars.
Thanks very much. Jeffrey Dobreiner. I am not a member. This is a bit of an unfair question because I know you're the Lunar Surface Innovation Consortium, but you didn't mention Gateway at all, and I'm just curious about sort of the potential, both, I mean, I guess mainly from an infrastructure standpoint, but also from a sort of a science mission standpoint. Lunar Gateway Space Station, what are your thoughts?
Right, yeah, so I will say it's a tricky question of like where the surface stops and where it goes. And some of the technologies like dust, for instance, unquestionably impact. You're going to take some of that with you when you go to Gateway. And so there are requirements being derived from, you know, the sorts of Gateway technologies that are being developed, things like the interfaces and so on. So we are working to understand what complications, in particular the dust, will have on Gateway being a sustainable entity as well. That's kind of where it's most important for me to understand it. I think a lot of the infrastructure won't go through Gateway, right? So that's really just going to be the astronauts and samples and things. But the big scale stuff will be delivered on CLPS landers and things like that, where we'll be using most of that commercial infrastructure, which, as we've seen, can be extremely powerful at doing this. And the CLPS landers are all starting to get a little bigger, and I think the expectation is they will continue to grow in their capabilities as well.
Okay.
I'll just answer from the science side, sorry. Lunar science side, at least. My candid answer is that we don't need the Gateway. Totally fine. Let's skip it and go straight to the surface.
NASA grant just got canceled.
I'm not a NASA employee. I can say such things.
It's okay.
Fair enough. Thank you very much.
We have 2 questions from the web. Joe Dura, non-member, asks, rather than average light intensity, can you create a map of regions that maximize the fraction of a month that has any illumination to determine the most favorable place for a habitat at the South Pole?
Absolutely. Yeah, absolutely. And in fact, if you want to play around with these tools, you can go to Quick Map. Just Google Quick Map LROC ASU. You'll find it very, very quickly. There's a whole host of parameters that you can look. Some are which are, you know, direct measurements. Some are derived. Yeah, so understanding and optimizing over the constraints that you have, not just from illumination, but also in terms of where you can land, line of sight to Earth so you can communicate back home. There's, you know, access to the scientific objectives that you have. There's a whole host of parameters that go into selection of those landing sites. I will say, you know, I think Brett and I are in pretty strong agreement about which one we really like, and that's the Connecting Ridge.
True, although I don't think science will drive that final choice.
We have another question from PSW friend Jorge Aponte, who's not a member of PSW. He's wondering, why did the moon not develop an atmosphere?
The moon may have...
It does have an atmosphere.
It does have a surface-bound tenuous exosphere, which some people study. This whole
surface-bound
thing, yes.
tenuous exosphere.
Yeah, exactly. It's an exosphere. At one point, it may have had more of an atmosphere, especially very, very early on when there was the magma ocean. But there were probably enough volatiles released from some of these massive flood basalt eruptions that didn't get to talk about that part, but huge volcanic history on the moon. And so there likely were periods of transient atmospheres on the moon. But in general, couple reasons. The moon's gravity is too low, and then it does not have an active dynamo, so it doesn't have a global magnetic field. The solar wind can strip off any atmosphere that's there.
One little stinger on that is that, you know, it's a bit of the vacuum around the moon is better than that in Leo. So if you think about how much extraordinary effort would go through terrestrially to create vacuums to do all sorts of manufacturing processes, you've got it for free and then some on the moon.
I like to tease my friends who study the exosphere, but there are very important processes you can learn about from studying it.
My name is AJ. I'm a new member, sort of a month old, actually. And one of the things that I have also seen, that Chang'e 2 also saw some thorium on the moon. And the question then is that with this thorium up there, and a possibility of a molten salt reactor working thorium bred to uranium-233, and that really, doesn't require high pressure, just high temperature, etc. And the other thing is that if this is now, NASA is of course looking into space propulsion, nuclear space propulsion, etc. These type of thing with the thorium reactor, or thorium or uranium-233 reactor, can be repurposed for energy on the moon. It can be a propulsive device, but then the reactor part can be taken. This is really very interesting. And the reactor part can be taken and then produce energy and also heat the regolith and all those kinds of things. And it also has, as a third meaning, obviously we have enough thorium in this country to give us power for 600 years. Electric power, all the energy that we need. So there is all these kind of things which are all, if we can solve that one thing that could be useful for the moon, Mars, space propulsion, and terrestrial, why not do it?
AJ is a proponent of thorium nuclear reactors.
I guess that's obvious now.
And an expert on it.
It's a very fair question, though. I think that one of the tricks of sorting out the technologies that NASA will do, often, sometimes the proposals will come out and seem almost too prescriptive, like they're presupposing what solutions they'll have. I have seen now more of a motion on the NASA side to have calls that are a little bit more asking industry to come and give them their suggestion. Our forum that we have, member of our consortium here, I didn't really talk much about the consortium, but we have now more than 2,000 members in our Lunar Surface Innovation Consortium, whole ton of industry members. Those sorts of suggestions go into these changes and can change the way that we're actually trying to fund these technologies so we can get the best things out of them rather than saying we've got the solution. It's kind of what I was trying to get at when I was saying, we're in the era where we're doing spin-on technologies and not spin-off technologies. So that's a point well taken. I will say that I think that, again, this is very, very early in the stages of space nuclear fission in particular. So I think the solutions that we'll be going after at first will be as simple as we can get, hopefully, and in part be done to test the regulatory framework for actually flying some of this stuff. And that might be an interesting point where if you're talking about lunar-sourced materials, you can get around some of the complications of actually launching huge quantities of uranium, for instance.
Yeah, and I just I forgot to mention that you guys at LSIC are doing a terrific job of putting it all together.
Yeah.
So thank you very much. And my calculation showed that 1 kilogram of thorium on the moon can give you 2 megawatt power for one whole year.
Yeah. So 2 megawatts is actually a really interesting scale because that's about where you get. That's about the scale where industry could be producing, appreciable amounts of oxygen for propellant. So I envision sort of end of Artemis era being hundreds of kilowatts, sort of. If you think about an FSP, which is like the Mars Forward Fission Reactor, being 40 kilowatts, plus a half dozen vertical solar arrays at 10 kilowatts, you're already pushing that 100 kilowatt stage. So then you're like ISS scale. So understanding the handoff then and what industry needs to take that and do more with it, that's kind of the stage that we're at right now.
We're going to take a question from one of our webinar participants, David Rabinowitz. David, can you turn on your mic and ask your question? David,
thank you, Larry. Yeah, I am a member, and I was wondering, you both mentioned the hope that this program will continue beyond administration, from one administration to another. And history doesn't seem to be very good from that point of view. I'm wondering, by the time things are really getting advanced, private industry will probably be ready to take over the whole thing. And have you thought about transferring or working handing off some of this stuff to private industry?
Yeah.
And what is the current legal situation, restrictions and such, about private industry actually going to the moon?
Yeah, so I would say absolutely. The stage that we're at on the NASA side is absolutely to look into commercial involvement as much as possible. Public-private partnerships to develop the technologies and try to look at where NASA can be in a follow position as opposed to a leading position. I think that's absolutely where we are. And the point where industry can take over is like one of the most central questions that we're trying to answer with a lot of the activities that we take on with our consortium. So that's, you're spot on. That's where we're trying to take it.
Hello, my name is Ilya. I am not a member, but I have a question that's not so scientific, but in terms of like the public and like Hollywood, are there any shows or movies that get like the NASA or the moon terraforming right, like The Expanse, Ad Astra, For All Mankind, and what are some of the biggest misconceptions from the public of like terraforming the moon?
I have to admit that sci-fi is not my typical genre, but I'll say I did watch a fair bit of For All Mankind. I mean, how can you not watch at least some of it? And I think that they did some things right. They talked about the permanently shadowed regions. I think that they got some of the contentious back and forths, those things kind of right. You're not going to send astronauts into those PSRs, though. No way. It's like, it's so cold, you're not going to happen. I don't really don't think that's going to happen.
It's like 60 Kelvin.
60 Kelvin.
In there.
Like, sending rovers down there is hard, right? So that's one thing that's often wrong. I think the thing that's consistently wrong, at least when I watch science fiction, is underestimating the scale and the difficulty and the true austerity of these sorts of environments. Space is empty, it's hard, and it's real big.
My name is Al Ehrlich, and I am a member. I know you haven't addressed this in your talk, but we know what happens to the body at Earth gravity, and we know what happens to it at microgravity, which is essentially zero gravity, and we know for durations up to a little less than a year, maybe. First of all, what is the intent of the program? To occupy the moon with a single individual for multiple years, or to shuttle the people? And if it's the first, is the effect of lower gravity on the human body well enough understood that you can project the effects without ever having measured it?
Sure. I mean, the start of the program will be not very long duration stays. It's going to start at a week and then maybe 2 weeks, up to 30 days or so. And so any kind of base camp is typically described as human-tended, kind of like the gateway will also be human-tended, not like permanently occupied. So I think the plan there is to develop that understanding and that knowledge gradually as you go along through this program. And NASA is standing up a lot of new research. They have a whole biological and physical sciences division where they are studying this now.
Do you know if gravity is understood, gravity's effect on the bones, for example, is understood well enough?
No, I don't think it could be. No,
it's not.
So,
Okay.
and you know, this is a big issue because if we're going to go to Mars in a decade or two, 2 or more plus, right?
Yeah, of course.
Realistically even more, you got to know because those are not short missions, right? So that's another thing where we're having, you know, close access to lower gravity and you know, easy access to get back home to study and figure that stuff out is really crucial.
Bob Hershey, I'm a member. Following up the last question, what is the overall plan that people have talked about for how many people up there and for how long and what they're doing?
Yeah, I mean, this evolves quite rapidly, and I think that we don't really know what it's going to look like past Artemis 4 or 5 and so on.
Yeah, I almost included the full kind of notional manifest of everything NASA will be doing at the moon up through, I think it goes through about 2030 right now. But even when it is shown, they say, all right, like look out through maybe 2025 everything past that is just kind of, you know, like they stuck some more little things on the chart at this point. So it's going to take a while to get that full plan. And the real goal here is to develop things in a kind of incremental way that builds upon itself. The knowledge builds upon itself, the systems, the infrastructure. It can all be developed so that nothing is a one-off. It's all building in that direction. And if the time scale takes longer because of budget changing, things like that, it's going to be able to sustain. It's going to be sustainable through those kinds of changes.
One more point that I want to add on to this is if you think about the time that it took to go from the first commercial crew to the first private astronaut mission, it's like, what, a year or something like this? It's an incredibly short period of time. So I can envision that one of the first things a commercial will want to do once we've landed astronauts on the moon is sell tickets to go back again. I mean, you'll use the same infrastructure, the same technology. It'll be proven. It'll be an extraordinary experience for anybody who could, you know, could and want to do that sort of thing. So I think that, you know, NASA will do what it does in service of exploration mission, and what happens adjacent to that is still to be known and actually pretty exciting to think about.
So a related question. So the first contract NASA let for a vehicle to land on the surface of the moon with humans was to SpaceX. And it is kind of a derivative of the Starship. Did you hear how many people it's supposed to carry? Notionally, because right now it's probably on paper.
Yeah, I mean, the error bars have got to be huge, so order of magnitude, you can guess, maybe?
What are they kind of thinking?
I mean, right now it's 2 crew.
Yeah, two crew is what, yeah, so that's what NASA's planning to do.
It's
but
too big for 2.
Well, it's scalable, right?
Yeah.
So at first, it's not going to be a fully developed rocket. It's going to be, I mean, it will be a fully developed rocket, but it's not going to be fully built out to what its ultimate planned potential is.
And I think the real advantage in a Starship lander is the downmass that it gives you to do all of this infrastructural work. And even in its own, like if it's going to stay there and not come back, or maybe not all of it comes back, you know, you can use that too. Like the what you can land really with something like Starship really changes what you could do.
And another important piece of that is that NASA has just the proposals have just been submitted for the second human lander system. So having that kind of competition, not relying on a single source, will be important for the long term too.
Yeah, by the way, for people who are interested in what it takes to get a mission to moon, there's a book about Lunar Prospector by, I think his name is Binder. I'm trying to think of his name. It's about 1,000 pages that you have to slog through. And about 500 pages is him relating the difficulties and how he had to repeatedly convince people they didn't need 3-axis stabilization. He could rely on spin, that it was supposed to be a low-cost mission. It's a very interesting book, except for the whining about how hard it was.
And that one was so creative because it was partly a Department of Defense mission, too. So they were really reaching to get the funding.
Yeah.
Yeah, it got lucky because there were those failures. And then the new NASA, what do you call them? The head of NASA wanted something quick, fast, and reliable. And this thing had been in gestation for like 10 years.
Yeah.
And he could present it, and they looked at it and said, oh, we can do this for cheap, and it's likely to succeed.
Yeah.
So, but it's a very interesting book from that standpoint. Yeah. Anyway, we thank you so much for this, that we have some gifts. And what this is a reprinted copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, now more appropriately known as PSW Science. It covers the period from March 1871, when it was founded, through June 1874. And it has very short reports, for the most part, on what was said at these original meetings. So I think I mentioned, you can find a little article on how to calculate the ratio of the diameter of the circumference of a circle, a number we commonly call pi, And this was a very nice method at the time to get you out to 30 decimal places, as opposed to 3 times 10 to the 12th decimal places. So then it also has a list of the founders and why they founded the society and why they called it the Philosophical Society of Washington, which for them was primarily science. And thank you very much for giving the talk.
Thank you.
And before you go, we have a few closing announcements. Fewer closing announcements that we might otherwise like to tell you. So all I'm going to tell you about the upcoming spring schedule is that the first meeting will be on January 20th. It will occur right here at the Cosmos Club with a reception, a dinner, and a lecture. And it will probably be our president's dinner and address. Finally, let's thank our crew for producing this meeting, streaming and recording the program, and editing and posting the video to the PSW website and the PSW YouTube and Vimeo channels. Cameo Lance, who capably produced and read the minutes. Robin Taylor, who you can't see because she's back there behind all the equipment, but she does the video, sound, the live stream, and the Zoom. Jared McQueen over there on my left, and Lloyd Mitchell over my right on those cameras. Ann McQueen, who capably handled room management, Rosette's live stream, and chat. Jobs usually done by more than one person. And Bill Mitchell, who's not here, who you won't see, and who hasn't done anything yet. But he will be editing the video that we will post as soon as he's done with it, probably Sunday night or Monday. In the meantime, the raw live stream will remain up on YouTube for everybody to watch. And with that, I will accept a motion to adjourn the 2,469th meeting of the Society to the social hour and to the refreshments in the back. Do I have a second? Do I second? All in favor? All opposed? The meeting is adjourned.